refraction, the bending of light as it goes from one medium to another at an angle, to help you prepare for Thursday's quiz. Now, I'm going to be messing on your screen. You can see a simulation. The link to this simulation so that you can mess around with it and do whatever you want is in your folder. It's in your refraction unit folder. It's the second link from the top, so it's right beneath the learning targets for this unit. So feel free after this demonstration or instructional video, whatever you want to call it, feel free to go to that and mess around with this and play around with this any way you want. Okay, so right now we have one of the requirements being met for refraction to occur. You can see that this right here is a light source. This red line is a beam or ray. You can see up here in the corner a ray of light. And I can change the angle of that light source here. Now, you might be asking yourself, well, Mr. Morgan, why is it not bending? Isn't it supposed to bend when it hits a new surface? Yeah, except the two materials separated by this solid line, right now I have them both set to air. So no, it's not going to bend because the medium doesn't change. In order for the light to bend, it has to speed up or slow down, which means it has to go from one medium to another. Right now it's going from air to air, which is really nothing. So let me change this second medium to glass. And you can see two things happen. Number one, well, three things. Number one, they change the shading so that you can tell, oh, hey, now it really is different. But two things happen to the light. First of all, some of it reflects off the surface, and that always happens. That's not really what we're talking about this unit. We did reflection last unit. But it's important to remember that that does happen to some degree. And if you measured this angle here and this angle here, you would see that they're equal because the angle of incidence equals the angle of reflection. But really, this unit, we're talking about the bending of light when it enters a new medium at an angle. So here's the angle. This is the angle of incidence, or theta 1, and here is the angle of refraction. So you can see, and especially when you are doing this, you might want to grab this protractor and put it up right in the middle here. Line it up perfectly on that surface and normal. Okay. You can see that the light ray coming in is coming in at 30 degrees from the normal. And you can see down here that the light ray in the new medium is less than 30. Because what has happened? Well, the light is bent towards the normal. That's what this kind of bending means. It didn't go straight. Straight would have been coming out right at 30. It bent towards the normal, meaning this line got closer to the normal in the new medium. And that's why this angle is smaller. And in fact, it looks to be right about 20 degrees, right? These little hash marks, each one of the little ones is 1. You can't really see them well. This is 5. This one here is 10. Another little one is 15, and that's 20, 25, and 30. Okay? So the light has entered from air to glass at an angle of 30 degrees, and the angle of refraction is about 20 degrees. Now, what I'd like you to do right now is press pause, and I would like you to go practice using Snell's law with this information. N1 in air is 1. The angle theta 1 is 30. N2 in glass is 1.5. Calculate using Snell's law and see if you get about 20 degrees. I'm going to ask you to do this on the quiz on Thursday. Practice doing it now and see if you get this. All right, go ahead and press pause and then come back when you're done. So did you get about 20 degrees? You know, depending on how you round off, it might have been 20.3 or 19.8 or somewhere around there, but it should have been right around 20 degrees. All right. Now, watch what happens as we change the angle of incidence, as we change theta 1 up here, and we increase this angle to 40. Okay. So what you'll see is that this angle got larger too, right? Before it was right around 20. Now it's maybe around 26. It's still bending towards the normal. It's still less than this angle. This angle up here is 40. This is still less than 40, but it's bigger than it was before because as this angle gets larger, this angle down here gets larger. Okay. So the angle up here, theta 1, the angle down here, theta 2. And when you're working with this, you can do as many of these as you want. You can press pause on your own simulation and go off and do a Snell's law and calculate to see if the numbers work out. Now, I'm going to do something neat here. I'm going to go right over here to this material. And instead of having glass at 1.5, I'm going to switch it to water. And you can see water right up here. All right, I'm not going to click on it yet, but water is only 1.33. So we're going to go from glass with an index of refraction of 1.50 to water with an index of refraction of 1.33. So I want you to predict when I switch it to water from glass, right now it's glass, when I switch it to water, will this light, I'm not going to move this is not going to change. Will this light beam get closer to the normal? In other words, will it bend more in the water than it does in the glass? Or will this light beam get farther from the normal? In other words, will it bend less in the water than it does in the glass? So is it going to bend more in the water and this light beam gets closer to the normal? Or is it going to bend less in the water and this light beam gets farther away from the normal? That might be a question I ask you on Thursday. So take a moment, maybe press pause, think it through, and predict your answer. All right, did you predict your answer? Is it going to bend more or less? Let's see. What happened? Did it bend more or less? Oops, it went back to water. Nope, sorry. Yeah, that's right. So look at it now. This is 60 degrees. What is that? It's a little more than 40. What was it before when it was glass? It was more, right? It bends less in the water. Not a lot less, but it bends a little bit less. Because in water, light doesn't slow down as much when it goes from air to water. When it goes from air to water, it slows down, but not as much as it slows down when it goes to glass, because glass has a bigger index of refraction. So it slows down more, which means it bends more towards the normal. All right, I'm going to do one more change here, okay? This time, I'm going to go back to where we were in the beginning, where it's air to air, all right? I'm going to move this back up here to 30. And this time, we're going to start in water. And we're going to go to air. Mr. Morgan, how would this happen? You never have water over air. Yeah, I know sometimes. But sometimes you've got a light source that's underwater and the light is trying to get out of the water. Maybe there's a diver underwater with who's diving at night for whatever reason. They've got a light, or maybe they're diving deep and they need a light bulb of some sort in order to see the things that they're diving to find, buried treasure or whatever. So what happens to the light beam when the light goes from water, n equals 1.33, to air, n equals 1.00? Well, it's going to speed up. Light speeds up when it goes to a medium where n is smaller. Light goes faster in air than it does in water. So when it speeds up, which way does it bend? Well, look at it. It bends away from the normal. It bends away from the normal. This angle down here is about 37, 38 degrees. This angle's 30. This angle is bigger because the light speeds up and bends away from the normal. Go ahead and do your Snell's law. Go ahead and press pause and do Snell's law and see what happens. When N1 is 1.33 and theta 1 is 30 degrees, N2 is 1, what do you get for theta 2? And you should get around 37 degrees. I'm going to wrap up this demonstration right there because I've said all I needed to say. Like I said, you can go to the link on Schoology in your refraction folder. It's the second link from the top. You can pull up this screen and you can do all this stuff. You can mess with it just like I was, do all kinds of things. And I would suggest, in preparation for Thursday's quiz, you spend some time practicing using Snell's law. Now, The one additional thing I'm going to say, and I'm going to include this in the update. If you read the update, you already saw it. I'm going to ask you specifically to practice for Thursday's quiz by doing problem number 67 on page 509, problem number 67 on page number 509. Also, when you finish the question they ask you to do, I would like you also to find the speed of light in that liquid. If you don't know what I'm saying, you'll know when you read the question. So do problem 67, page 509, but also add another part to their question from the book and calculate the speed of light in that liquid. Okay? All right. Good luck. And we'll have a quiz on Thursday. Thanks, everybody.